Hello everyone, I am Tanma Sharma, a Prime Minister's Research Fellow from Mechanical Engineering Department of IIT Patna, and I welcome you all to today's tutorial session for the NPTEL course IC Engines and Gas Turbines. In today's lecture, we'll be learning about different jet engines, learning the concepts, and we'll be deriving the turbojet engine part, thermodynamical expressions for thrust, propulsion, efficiencies, and we'll be solving a few problems and concluding the lecture. So without further ado, let us start today's lecture. So jet propulsion. So what is a jet propulsion? So jet propulsion, the principle involves that imparting momentum to a mass of fluid in such a manner that a reaction of the imparted momentum provides a propulsive force. So that is just as Newton's third law. If a force is applied upon a particular substance, then equal and opposite force is applied back to the source of the force. In that way, jet propulsion is achieved. So it may be achieved by expanding the gas, which is at high temperature and pressure, through a nozzle, due to which a high velocity jet of hot gases is produced in atmosphere that gives a propulsive force in the opposite direction due to its reaction. So that we can well visualize. Um, so if there is a nozzle and it produces gas at very high velocity and it ejects the gas to the atmosphere, then a particular thrust will be imparted from the atmosphere back to the nozzle, which drives the nozzle in the forward direction or the direction opposite to where the gases are released to the atmosphere. But that's the reaction due to the expulsion of the gases. And we use that reaction of the gases to propel our aircrafts in the atmosphere. And for jet propulsion, open cycle gas turbine is found to be most suitable, and we will learn why. Before that, let us see the types of air steam jet engines. So basically, there are three types: turbojet, turboprop, and ramjet. These engines are air breathing engine, meaning they breathe in air, means the air goes inside, there will be a compressor, or in case of ramjet, there will not be a compressor, but there will be directly a diffuser in which the air will be sucked in, and that air will finally the enthalpy of that air will be increased, and the velocity will be increased by the fuel that is burning inside the whole system, whole engine. And as per the kinetic energy which is uh, imparted to the jet of air, that air will be released in the atmosphere, and the thrust will be obtained by the change in the kinetic energy which was imparted due to the burning of the fuel. So that way, since air is entering inside the system, these are the air breathing engines. Then these are steady combustion systems are possible out here. The combustion system in which the fuel is burnt are occurring at a steady state, and there is continuous airflow. Unlike the reciprocating engines, the engines that we have, the spark ignition and the diesel engine, in which there will be reciprocating action and there will be a particular suction stroke in which the air will be sucked in. But air, on contrary, in these jet engines, there will be continuous supply of air, and as per that, this the thrust and the propulsion is achieved. Now, let me tell you an interesting story. So, back when, uh, very during the World War II or even before, the aircrafts which were used, they use a screw propeller, and the air propulsion was achieved by a screw propeller. And the screw propeller is this kind of arrangement that you can see at the front of the aircraft. And this propulsion of this itself creates a thrust and we will see how. So in this system, the total power developed by the turbine full expansion is used to drive the compressor and the propeller. So there will be a turbine system, and you will see this. This is the turbine system. This is the propeller that you can see in here. The air will go inside the compressor, which will be again helped by the propeller, and these all are in the same shaft. So the turbine, in the turbine, the energy which is produced is driving the compressor as well as the propeller. And here the turbine, the uh, gases are exhaust to the atmosphere, and the thrust is produced by the propeller. So you see, by controlling the supply of the fuel in the combustion chamber, the power supply to the propeller can be controlled. Yes. So by supplying lesser fuel, lesser amount of work done will be produced in the turbine, and accordingly the RPM will be reduced. Higher amount of fuel will create higher amount of work done. Accordingly, high amount of larger RPM can be achieved here. So by controlling the fuel supply, we can control the power, and the rate of increase in efficiency of a screw propeller is higher at lower speeds. So at lower speeds, there is high efficiency, but the efficiency falls rapidly at higher speeds above sonic velocity. So it cannot be used for supersonic cases. And for supersonic cases, we have ramjet, and we will learn about that too. So these were the systems which were used previously and were found a little bit inefficient in compared to today's system. And for today's system, we will be studying these three systems, the turbojet, turboprop, and the ramjet, and we will see how these are designed and what are the advantages and disadvantages of this. So let's start by introducing the turbojet. A turbojet engine consists of a diffuser. So this is diffuser at the entrance, which slows down the air entering at velocity equal to the plane speed, and part of the kinetic energy of the airstream is converted into pressure, and this type of compression is called as the ramp compression. So what happens is that this is the whole engine. It will start moving in this direction of the aircraft, okay, and then the air will come inside the compressor. Before going inside the compressor, it will go inside a diffuser, in which there will be more pressure build up, and the kinetic energy will be reduced, and then it will go inside the compressor, where the pressure and the kinetic energy both will be increased partly. And as per that, the pressure in the whole system will increase, and then the air of higher pressure, and the pressure will be around 3 to 4 bar, will go into the combustion chamber. The combustion will take place, go into the combustible gases at higher enthalpy will get expanded inside the turbine, and the exhaust from the turbine will go inside the nozzle, and from the nozzle the kinetic energy is the pressure energy will be converted into kinetic energy, and it will the gases at very high velocity will be sent to the through the exhaust to the atmosphere, and that velocity of the gases will finally impart a thrust upon the uh, aircraft in the direction of the aircraft. So that's the whole summary of it. Now let us visualize this in detail. So the air is compressed to a pressure of 3 to 4 bar in this rotary compressor, and this is usually an axial flow type of compressor. Then the compressed air then enters inside the combustion chamber, where the fuel is added. The combustion will take place at sensibly low constant pressure, and subsequently the temperature rises rapidly. So with the temperature, yes, obviously the enthalpy also will rise, because this is a constant pressure process. And then the hot gases then enter into the gas turbine, where there is a partial expansion which takes place, and that expansion, the power produced due to that expansion, is just sufficient enough to drive the compressor and the fuel pump, so fuel pump delivering the fuel here, and other auxiliaries inside the aircraft. So the turbine produces enough work only to power up these systems, and uh, you will see that the shaft connecting the turbine and the compressor is not connected to the nozzle, and so the turbine work is entirely used upon that, and the exhaust which is coming up also has the remaining enthalpy, and that remaining enthalpy, so the exhaust gases from the gas turbine which are at higher pressure than atmosphere are expanded in the nozzle, and a very high velocity jet is produced, which provides a forward motion to the aircraft by jet reaction. So you see, if the jet of gas is expelled in this direction due to Newton's third law, an equal and opposite force will be applied in the opposite direction, that is the direction at which the aircraft moves. Mm. So at higher speeds, the turbojet gives higher propulsion efficiency. The turbojets are most suited to aircrafts traveling above 800 km per hour. And let me give you a perspective. So the speed of sound is around 1200 km per hour. And here the turbojets are most suited to travel above 800 km per hour, but still it is not used typically to move at supersonic speeds. So it is below sonic, at the sonic level the turbojet engines are used generally. The overall efficiency of turbojet is the product of thermal efficiency of the gas turbine plant and the propulsive efficiency of the jet nozzle. And we will learn about this in later in the derivation of the turbojet engines. Next, we learn about the advantages and disadvantages of turbojet engines. First, let us talk about the advantages. So the construction is much simpler as compared to a multi-cylinder piston engine of comparable power. So a multi-cylinder piston engine like we have in our cars, that is a little bit more complicated and sophisticated as compared to the turbojet engine, because you see the compressor and the diffuser at the start of the compressor, these are all connected at the same shaft as that of the turbine, and there is a fuel combustion chamber attached here, and this arrangement is quite simple in comparison to uh, the the piston engine cylinder that we have in our cars. And everything is rotating, so there is no reciprocating action, that is quite simple to manage. So engine vibrations are absent because the reciprocating actions are absent, the vibrations are very less, and that is very uh, beneficial for the cases at higher speeds, because if the vibrations are very high, it will develop unnecessary um, these moments, and that may break the whole system, and so such high risk will be involved. Then much higher speeds are possible, more than 3,000 kilometer per hour can be achieved. So why it is so? Because everything is rotating, so there is no reciprocating action. So if there will be reciprocating action, then such high speeds cannot be achieved. So everything is rotating, that's why we can achieve very high speeds, and that is very suitable for aircrafts. Then power supply is uninterrupted and smooth. See, the whole process is continuous. There is no suction stroke, no fuel delivery stroke, no combustion stroke differently. So the fuel is continuously supplied, it is burned, and it is taken away, the gas taken away to the turbine. And this is a very continuous action. And due to that, the power supply is uninterrupted and smooth in comparison to a reciprocating type, in which the power stroke is produced, to say for a four stroke, the power stroke is only 25% of the entire cycle. So that way there will be a flywheel which will store the energy, this rotation energy, and it will impart in the rest of the strokes. And these kind of things are not required in turbojet engines. Then the weight to power ratios are superior. Yes, the weight to power ratios are quite superior, and as compared to that of the reciprocating type or aero engine, the rate of climb is higher. The requirement of major overhauls is less frequent. Yes, because the manufacturing, the constructions are quite simple, and the parts involved are quite less and less sophisticated. So if one of the part, even if it fails, to replace that part, a major overhaul is not required. Then the maximum altitude ceiling as compared to turboprop and conventional piston type engines. And why it is so? Because due to very high RPM, low density air at very high altitudes can be also supplied sufficiently in order to maintain that air fuel ratio. And due to that, a maximum ceiling altitude can be achieved by the turbojet as compared to turboprop and conventional piston type engines. The frontal area is small and fuel can be burned over a large range of mixture strength. So that gives the flexibility upon the power to be delivered by this engine. The disadvantages of turbojet engines are it is less efficient compared to the other engines, other jet engines. Then the life of the unit is comparatively shorter. So since the entire life as compared to the reciprocating type engine, so that is quite less, then the turbojet becomes rapidly inefficient below 550 kilometer per hour, and we will see why. There is a formula by which the efficiency is calculated. Then it is more noisy than a reciprocating engine, and materials required are quite expensive, obviously. Then requires a long strip since length of takeoff is too much. So this aircraft needs to attain a particular velocity before it can take off, before it can generate the velocity of its own, and it can take off the flight. Enough thrust is enough lift force is created, and that uh, needs a lot of time, and for higher time, higher distance it needs to cover, and accordingly a longer strip is required. So for aircrafts which are landing at very low strips, such as the ships in ships uh, in our defense ships, some of the ships carries airstrips, and in the airstrips the aircraft lands, and it is a very small piece of a strip, not incomparable to the strips air strips we have in the airports. In that cases, this kind of engine, the aircraft having this kind of engines cannot land or cannot be taken off from those kind of strips. That is quite inefficient. Then at takeoff, the thrust is low. This effect is overcome by boosting. So the thrust is quite low because the speeds are quite low, and these are generally overcome by boosting, and that's why since the thrust is low, we need a longer strip as well. So that was all about the turbojet engine, and we will learn about the derivation in after a few slides towards the later section of the class. But before that, we will learn about the other types of engines that are present. So this is the next is the turboprop engine. So here the expansion of gases takes place partly 80% in the turbine and partly 20% in the nozzle. So we have this the nozzle here. 80% of the uh, expansion of the gases takes place and 20% takes place in the nozzle. The power developed by the turbine is consumed in running the compressor. Okay, the 80% is used in the compressor and the propeller, which also have the diffuser unit. So the propeller and a jet produced by the nozzle give the forward motion to the aircraft. So due to the propeller also, there will be an outer casing like this, and here also there will be some velocity imparted to the air, and accordingly that will be also combined with the air gases coming out of the jet nozzle, and together it will give a give a forward motion to the aircraft or the thrust required. Then the turboprop entails the advantages of turbojet. Okay, that is low specific weight and simplicity in design, and the propeller, that is high power for takeoff and high propulsion efficiency at speeds below 600 km per hour or 550 km per hour. So our turboprop engine has advantages both of turbojet and the propeller. The propeller can give high power to the takeoff and high propulsion efficiencies, whereas for turbojet it can have low specific weight and simplicity in the design. So both of these advantages are incorporated inside the turboprop engine. Then the overall efficiency of the turboprop is improved by providing the diffuser before the compressor as shown. So in the diffuser, the pressure is raised and that increases the efficiency. The pressure is raised and the kinetic energy is decreased, and that we will see how it is affecting in the turbojet and how a diffuser can effectively raise the pressure. That the pressure rise takes place in the diffuser. The pressure rise takes place due to conversion of kinetic energy of the incoming air, and the velocity of the incoming air is equal to the aircraft velocity because the air in the atmosphere is not moving, rather the aircraft is moving. So relatively, if the aircraft is thought of stationary, then the air is moving in the opposite direction of the aircraft and at a velocity equal to the aircraft velocity. And the kinetic energy of the incoming air is converted into pressure energy by the diffuser. And this type of compression is known as the ram effect. And that is quite used in the turboprop engine. Next, we have the ramjet engine. A ramjet is also called as athodite, Laurent tube, or flying stovepipe. The ramjet engines have the capability to fly at supersonic speeds, and we will know why. So in a ramjet, what happens is that we have diffuser, but we do not necessarily need a compressor and a turbine. So you see, this is at the same line. We do not need any rotating parts. The air enters and there will be a subsonic diffuser which actually increases the pressure, and there will be a fuel injector which supplies fuel. There will be combustion and due to the igniter, and that will impart a very high kinetic energy to the gases, and there will be nozzle which actually will raise the kinetic energy from the subsonic to the supersonic level, and finally there will be exhaust. So a compressor and a turbine are not necessary as the entire compression depends on only on ram compression. So this is the ram compression happening at the diffuser. This is the ram compression, and the ram jet consists of a diffuser used for compression, combustion chamber, and nozzle. The air enters the ramjet plant with supersonic speed. So here this is at the supersonic speed and is slowed down due to sonic velocity down to sonic velocity in the supersonic diffuser. So there will be a supersonic diffuser, there will be a subsonic diffuser also. Consequently, the pressure suddenly increases in the supersonic diffuser to the formation of a shock wave. So a shock wave is produced over here. There is a sudden increase in pressure, right? From supersonic to, and there is a sudden change from the supersonic to the subsonic level, and that's why a shock wave is produced. The pressure of air is further increased in the subsonic diffuser, increasing the temperature of the air above the ignition temperature. Then, in the combustion chamber, the fuel is injected through the injection nozzles. The fuel air mixture is then ignited by means of a spark plug. So, here we have the spark plug or the igniter. And the combustion chamber temperatures are of order of 2000 Kelvin are attained out here. So, this is the combustion chamber at the downstream of the igniter, and a temperature of 2000 kelvins are attained out here. The expansion of gases towards the diffuser entrance is restricted by pressure barrier at the after end of the diffuser. So a pressure barrier at the after end of the diffuser, it restricts the expansion of the gases, and as a result the hot gases are constrained to move towards the nozzle. and undergo an expansion. So here they will undergo an expansion. The pressure energy is converted into kinetic energy due to the expansion, and high velocity gases leaving the nozzle provide forward thrust to the unit. And the best performance of RAM engine is obtained at a flight speed of 1700 km per hour to 2000 km hour. That is, if the sonic velocity is 1200 km per hour, then you can see how much it is at the supersonic level. So that was about the ramjet engine, and let us now know about the advantages and disadvantages of this engine. Basically, at ramjet, the advantages are it has no moving parts. If there is no moving parts, there will not be any frictional losses, and it will be more convenient uh, in terms of the energy that is produced. Then it is lighter in weight and has a wide variety of fuels. We can use a wide variety of fuels in the ramjet engine. Then the shortcomings or the limitations are it cannot be started of its own, obviously. So it has to be accelerated to a certain flight velocity by some launching device. So this has to be taken up at a very high velocity before it becomes functional. The ramjet is always equipped with a small turbojet which starts the ramjet. Okay, so the turbojet is actually responsible for the starting and getting up the aircraft at a particular speed, after which the ramjet becomes operational. And once when the ramjet becomes operational, it will increase the speed of the aircraft beyond the sonic level, that is in the supersonic region. Then the fuel consumption is too large at low and moderate speeds, obviously. So although a very high speed is attained, the fuel there is a huge amount of fuel losses. So in our fighter aircrafts that we can see, mostly they uses ramjet because they need to travel at supersonic speeds. So, but they are not able to move at a very long time because they require uh, refueling very frequently. So and that's why they cannot move at very high speeds for a very long time. For successful operation, the diffuser needs to be designed carefully so that the kinetic energy associated with the high entrance velocities is efficiently converted into pressure. And to obtain steady combustion, certain elaborate devices in form of flame holders, pilot frame are required. So these were the shortcomings and limitations of a ramjet engine. So till here we have learned about the various types of this basic classifications of air jet engines, that is the turbojet, the turboprop, and the ramjet engine. Next, we will study how we can derive for the thermodynamical expression for analyzing the turbojet engine. So let us see here. So we will have to thermodynamically understand the different processes associated inside a turbojet engine. So this is a turbojet engine which I have already shown to you. There's no propeller out here. Then this is the TS diagram, and you can also have a similar type of diagram in the HS diagram. So basically we will start from process 1 here, that is air coming from the atmosphere. So relative to the aircraft, so if the aircraft is moving at a velocity v, then we'll have to assume that the aircraft is stationary, and relative to the stationary aircraft, the air is moving at a velocity v inside the compressor. So that's how the point 1 is fixed. We have a particular state of the uh, air in the atmosphere, and from that we will start our analysis. So process 1 to 2 is the air entering from the atmosphere is diffused inside the diffuser, and diffuse means it will be diffused isentropically from velocity c1 down to 0, that is c2 is 0 out here. And this indicates that the diffuser has an efficiency of 100%, but that is not the case. And this way, when the velocity is reduced to zero, and accordingly the entire kinetic energy is converted into pressure energy, that process is called as the ram compression. But the process 1 to 2 is not the actual process. There are some isentropic losses, and due to these losses, the process deviates from 1 to 2 straight line to 1 to 2 dash here, and there is an efficiency associated with the diffuser. Then process 2 to 3 is the isentropic compression of air. So here there is isentropic compression of air 2 to 3, but the process 2 dash to 3 dash shows the actual process because there are certain losses, heat losses, and accordingly 2 dash to 3 dash is the actual process. Now you will see that the path of 1 to 2 dash then 2 dash to 3 dash is higher than their isentropic path, that is 1 to 2 and 2 dash to 3. And this part actually means that amount of work that needs to be spent in the diffuser and compressor. So lower the part, lower energy needs to be spent over there. So that would be beneficial. But since there are losses, we need to spend high amount of energy in order to get the same effects, that is the same diffusion and the same compression. And in that way, larger amount of energy is needs to be spent, and there is an efficiency associated both with the diffuser as well as the compressor, and we will see how to use that efficiency in our later problems. Then 3 to 4, that is ideal case, is the ideal addition of heat at constant pressure P3 n equal to P4. The process 3 dash to 4 actually shows the actual heat addition, because this amount of heat is already been added by the uh, due to the losses, and 3 dash to 4 shows the actual heat addition of heat at constant pressure P3 equals to P4, and that heat is being added by burning fuel inside the combustion chamber. Then process 4 to 5 is the isentropic expansion of the gas in the turbine. However, 4 to 5 days shows the actual compression. Now you will see that the isentropic compression expansion 4 to 5 is a longer compared to its uh, irreversible part, which is 4 to 5 dash, which is shorter. This actually means the total work that is produced by the system. If there were no loss and it would have followed 4 to 5, higher amount of work can be produced by the system in compared to 4 to 5 dash, which is due to the losses which incur in the turbine. So there is also an efficiency associated with the turbine, as well as there is an expansion of the gas in the nozzle, and there is also an irreversible process to the isentropic process 5 to 6, which is 5 to 6 dash, the irreversible process, and there is also an efficiency associated with the nozzle. So these were the processes of a turbojet engine. Next, we will see how to derive the thrust and the propulsion. So before doing that, we need to analytically solve this particular point. So we need to get these temperature points in order to later on derive the thrust, the propulsion, energy, the efficiencies, etc. So we have to see each component differently. And first, let us take the diffuser. So the diffuser operates between state 1 to 2, and the steady flow energy equation is written as Ca square by 2 plus H1 plus Q12 equal to C2 square by 2 plus H2 plus W12. Here Ca is the velocity of the air coming inside the compressor, which is equivalent to the velocity in which the aircraft is moving, or the velocity of entering air from atmosphere. And for an ideal diffuser, C2 would be 0. Q12 will be 0 because there will be no heat losses associated with this, and work done will be 0, work 12. But we do not have an ideal diffuser, right? So enthalpy at state 2 is H2, equals to H1 plus Ca square by 2. So that will be the ideal case, but there is an efficiency associated. Also, if we convert the enthalpy into temperature, because we know enthalpy equals to Cp into T, where Cp is the specific heat at constant pressure, we convert that and we will get the temperature, this relation between the temperatures, that is T2 equals to T1 plus Ca square divided by 2Cp. Next, we'll actually have to calculate the actual process, the temperature raised during the actual process. So for that, since we now know the temperature T2, we can use the efficiency of the diffuser like this. So efficiency of a diffuser is H2 minus H1, which would have been the ideal case divided by the actual case, which is higher than the ideal case, that is H2 dash minus H1, and that will be equal to T2 minus T1 divided by T2 dash minus T1. And accordingly, we will have H2 dash equals to H1 plus Ca square divided by 2 eta d, and we can convert it into temperature as T2 dash equals to T1 plus Ca square divided by 2Cp eta d, where eta d is the efficiency of the diffuser. So that's how you solve for the diffuser case. Next, we'll solve for the compressor case. So in compressor, energy equation, we'll have to solve between states 2 and 3. That is states 2 and 3. Let us assume ideal conditions as first. Then we will solve for the actual condition, that is involving the losses. So for ideal condition, H2 plus C2 square by 2 plus the heat loss and the work done equals to H3 plus C3 square by 2. So now I will ask you one question. Why the work done is written in this side? Because in compressor, we need to do the work over there. So it is a negative work done. And since the value is positive, we need to put it out here in order to make up for the sign. So the actual work will be negative, and we'll have to, and WC refers to a positive value. That's why we put it in the left side of the equation. Next, we'll have to assume that the changes in the potential and the kinetic energies are negligible. The ideal work expanded in the running of the compressor, we'll have to calculate by assuming this. Now, where is the potential energy? So the potential energy, actually there is a term of JAD, that is the height of the state 2 from state 3, and if there is a change in height, then we have to account for that. But since this is an axial flow system and there is no change in the height, so the total change in the potential energy is also 0, and the kinetic energy is, so the change in kinetic energy is given by C2 and C3 terms, the difference between these. We also assume it to be negligible because there is negligible change in the velocity in the compressor. So the ideal work expanded in the running of the compressor can be given as WC equals to H3 minus H2, that is equal to CPT3 minus T2. Okay, but that is not the actual work. The actual work will be higher than this. So we'll have to compensate that by using the efficiency of the compressor eta C, and you can see the actual compressor work will be H3 dash minus H2 out here, or we can also see H2 dash. So H3 minus H2 divided by eta C, and that is CPT3 minus T2 by eta C, and eta C is the isentropic efficiency of the compressor. Next, we will solve the thermodynamic expressions in a combustion chamber. So in a combustion chamber, we have 3 dash to 4 in the actual case and 3 to 4 in the uh, ideal case. So we will see the ideal heat supplied per kg will be Q H4 minus H3, that we can all agree H4 minus H3. that is equal to Cp T4 minus T3. Then actual heat supplied is equal to 1 plus Mf by Ma into H4 minus H3 dash. Now why did we do this? So in H4 we do not have uh, air only, and every all the calculations are done per kg of air. So in the state 4 we have gas, the fuel that comes and gets converted into gas. So there will be a fuel air mixture at state 4 that we combinedly call it as gas, and that mass will be a little bit higher than the mass of the air which was present because of the involvement of the fuel, and accordingly the mass over here per kg of air will be given by this expression. So Ma plus Mf will be the total mass of the gas, and divided by Ma, that will result in per kg of air, and accordingly the actual heat supplied will be this term into H4 minus H3 dash. Next, the that is QA. If we uh, break the H4 and H3 dash into temperature terms, we will see Cpg into 1 plus Mf minus Ma, this is fuel air ratio, into T4 minus Cpa into T3 dash. So why Cpg? Because this is gas and the specific heats for gas will be different than specific heats for air. So where Cpg and Cpa are specific heats of gases and air at constant pressure respectively. So this was for the combustion chamber. Next, we will see for the turbine. So in a turbine, we'll have to solve between states 4 and 5, and the energy equation is given by H4 plus C4 squared by 2 plus Q4 to 5 equals to H5 plus C5 squared by 2 plus Wt. So C4 is the velocity at 4, and Q45 is the entire heat loss during the process or heat generated. Then H5 is the enthalpy at ideal condition at this state 5, and C5 square is the velocity at 5. So due to expansion there will be some change in the kinetic energy as well, and this is the work done. So if that expansion of kinetic energy is completely used for getting the work, then we can say that the Wt is the work done by that. So Q45 is 0 in the actual case if there's no heat generated in the turbine. And then the turbine work will be given by T4 minus T H4 minus H5 plus C4 square minus C5 square divided by 2. And if the change in kinetic energy is neglected, then we will have the work of turbine to be H4, only the enthalpy difference between 4 and 5, and CPT4 minus T5. The actual turbine work is between 4 and 5 dash, so there is an efficiency of the turbine that we can use here. So that will be Cp T4 minus T5 dash equals to T4 minus T5 into eta T, where this eta T is the isentropic efficiency of the turbine, and accordingly for simplification we will use turbine work to be equal to compressor work, because we can see that the compressor and the turbine are connected to the same shaft, and that's why we will equate these two, and the while equating CpT4 minus T5 dash equals to CpT4 minus T5 into eta T, or CpT3 equals to CpT3 minus T2 divided by eta C, the compressor work. So T5 dash will be T4 minus T5 into eta T equals to T4 minus Cp into T3 minus T2 divided by eta C. So if we need to find out the temperatures, then we can equate these two and get the temperature values, which will be later useful for if the question comes as what is the turbine work done. So we can directly calculate based on the temperature value. So that's why this derivation is quite important. Now the turbine is done. We are now only left with the jet nozzle. So for the jet nozzle, the energy equation between states 5 and 6 we need to see. So the steady flow energy equation is given as H5 plus C5 square divided by 2, because H6 plus C6 square divided by 2, that is the ideal case. Next, for the actual case, so we have H5 dash plus C5 dash squared by 2 equals H6 dash plus C6 dash squared divided by 2, the actual case. Then if C5 dash square is way less compared to C6, because inside the nozzle the kinetic energy will be increased tremendously, so we can ignore the inlet velocity or the inlet kinetic energy of the gas. Then if it is ignored, then we will have H5 dash equals to H6 dash plus C6 dash square by 2, and that will be C6 dash equals to 2 into H5 dash minus H6 dash root over. And finally, if we use the efficiency formula, and we will be able to compare with this value of H6, and accordingly we will convert the enthalpies into temperatures by using the specific heat, and this will be the specific heat of specific heat of gas at constant pressure, and we will get the value of the final velocity of air that is coming out from the jet nozzle. Sorry, not air, air plus fuel, that is the gas, and eta n is the nozzle efficiency out here. So the thermal efficiency will be H4 minus H6 dash, H4 minus H6 dash out here, minus H3 dash minus H1 divided by H4 minus H3 dash, H4 minus H3 dash. Why this comes? Because this part is completely in generating the work, or is the entire outcome from the power plant, gas turbine power plant. And this part H3 dash minus H1 is the entire part in which the energy is spent in doing the compression. So energy outcome minus energy spent divided by total energy that is given. So total energy which was given into the system is 4 minus 3 dash, in which the fuel was burnt and the energy was utilized. So that's our thermal efficiency, and it is given as this. Next, we will learn how to calculate the thrust, the propulsion energy, the efficiencies associated with other efficiencies with the turbojet engine. Okay, so here we can convert the thermal efficiency into the temperature components, as you can see out here. If we assume that the specific heats of air and the specific heats of gas are the same, then we can use this kind of formula. Now let us talk about thrust. So let us assume that CA is the forward velocity of aircraft through air. So the aircraft moves in this direction, the direction of aircraft, at a velocity of CA. We assume that the atmospheric air to be still the velocity of air, and relative to the aircraft at entry to the aircraft will be CA. So that is only possible if the velocity of the air is 0, the absolute velocity of air. And this is called as the velocity of approach of air, the CA. Next, let us assume CG equals to the velocity of gases relative to the exit nozzle of aircraft meter per second. So that is the absolute velocity, Cj, velocity of gases relative to the exit nozzle. Then 1 plus fuel plus air, that is the mass of products of leaving the nozzle for 1 kg of air. So here we have to use this because every calculation is done based on the mass of air present, and we have to utilize the mass of fuel in some of the cases when we are talking about gases. So this part is relative to that. Then thrust is the force is produced due to the change in the momentum and how the change in momentum is happening. So now the absolute velocity of gases leaving the aircraft is Cj minus Ca. So Cj is the velocity of the final velocity of the gases leaving the nozzle, but Ca is the aircraft. So relative to the aircraft, the absolute velocity of gases leaving the aircraft is Cj minus Ca, and absolute velocity of air entering the aircraft, what it will be. So air is entering at Ca, but again the direction of aircraft, the velocity is Ca. So that's why the absolute velocity of air will be 0, right? So that's how we will see. So even if the Cj is the velocity of air moving out, we have to subtract by Ca because that's where the velocity of the aircraft is. Next, the change in momentum will be given as the mass of gases. This is the mass of gases per kg of air into the change in the velocity. And this is, since it is per kg of air and we are calculating per kg per second of air, so that is the change of momentum will directly give us the value of value of force, that is the thrust, Newton per kg of air per second. Now the kg of air per second, if we are given, we can directly calculate this value of thrust. So change of momentum. Now I would like to recollect this few of the concepts. Now unit of force is kg meter per second square, but change in momentum is this is kg and this is meter per second. So the net formula is kg meter per second. So that cannot be equal to the force, right? So that is the force per second of air that is passing in. So if the values would have been given in per kg or kg per second, then the change in momentum would have been directly giving the value of force. So the thrust is given per second, Newton per kg of air per second. So that's how the unit comes. So T equals to Cj minus Ca, that is Newton per kg of air per second, if we neglect the mass of fuel. And usually the mass of fuel is quite less, so we can neglect for very low amount of fuel that is used. Next, let us talk about the thrust power. Since we have the thrust in newtons, we can talk about it in power. We have to just convert it to from newton to kilowatt. So it is defined as the rate at which work must be developed by the engine if the aircraft is to be kept moving at a constant velocity Ca against friction or drag force. So that is the thrust. The entire force is keeping the velocity moving in direction of the aircraft at a velocity of Ca. So that is the thrust power. And the thrust power is given the forward thrust in the force into the speed of the aircraft. So if we put in the formula, we will get the formula to be whole of the thrust force multiplied to the velocity of air. Next, this is the if the mass of fuel is neglected, we can write it in these terms. So this is if we have it in kilowatt, so kilowatt per kg of air. Then we have the propulsive power. So propulsive power is the energy required to change the momentum of the mass flow of gas, representing the propulsive power. So in simple terms, it is the expressed as the difference between the kinetic energies of the entering air entering and the exhaust gases. So if we are burning some fuel, we are giving some energy, and that energy is increasing the kinetic energy of the gases. So kinetic energy of the gases at the air at the start is mass of air into Ca square divided by 2, right? Half m into v square. So the v is Ca, right? And m is the mass of air. And that kinetic energy increased to that of the kinetic energy of gases. So half into mass of gas into the velocity of gas whole square. So that's where the kinetic energy is increased by adding by the combustion, the energy produced during combustion. So the difference between these two kinetic energy is given as the propulsive power, and it is given by the change in kinetic energy. So mass half into mass of fuel into the velocity of the gases minus half into mass of air into velocity of the air whole square. So velocity of the mass of air is taken as per kg of air, right? So that we have divided it entire expression, that is watt per kg, and then we can if we ignore the mf term, then we can directly get cj square minus ca square divided by 2. And finally, this is if we convert it into kilowatt per kg of air. Next, we have the propulsive efficiency. So that is the ratio of thrust power to the propulsive power is called as the propulsive efficiency of the propulsive unit, and that is given by thrust power by propulsive power. So this is the whole expression. So uh, here we have 1 plus mf by ma in the cj minus ca whole into ca. So that is the thrust power that we have, and this is the difference in kinetic energy, which is also given by the propulsive power. And if we simplify this equation, we'll find, so this is the simplified equation, and if we neglect the mf part, so we are left with only 2 divided by cj by ca plus 1. So it is very important to note, after all this simplification and assumption, that it is evident that the propulsive efficiency, so efficiency is this part, so it increases with an increase in the aircraft velocity ca. So if the ca increases and ca approaches cj, then 1 plus 1, it will be 1, the division, and 1 plus 1 is 2, and the propulsion efficiency, propulsive efficiency will approach to 100%. But the thrust will be reduced to 0 because cj minus ca will be reduced to 0, right? So and that's where, so at highest propulsive efficiency, the thrust will be the lowest, and there will be an optimization while the aircraft is moving. So that was based on okay, the last part is propulsive efficiency. So propulsive efficiency is given as the ratio of propulsive work and the energy released by the combustion of fuel. The propulsive work by the heat released by combustion. The propulsive work means increase in kinetic energy of gases divided by heat released by the combustion of fuel. We put in the formulas and we will get a value like this, uh, say cj square minus ca square divided by 2 into mf by divided by ma into calorific value, almost equal to that. Next, overall efficiency Ethernet is given by, so the thermal efficiency, the propulsive efficiency, and the thermal efficiency. So this actually it is the thermal efficiency. So that's a mistake, and that value gives us for maximum overall efficiency, the aircraft velocity CA is one half of the jet velocity CJ, and the jet efficiency is defined as uh, the final kinetic energy of the jet divided by isentropic heat drop of the jet pipe plus the carryover from the turbine. So from here, we have known about how to calculate the thrust, propulsive, the propulsion kinetic energy, the different efficiencies, that is the propulsive efficiency, the thermal efficiency, overall efficiency, the jet efficiency. So these are the parameters by which we can judge how good is an aircraft engine working. And we have also learned how to um, uh, how to get the values of the different states, that is the pressure and temperature of different states, inside a turbojet engine till now. So it is time to apply the knowledge that we have gained so far in solving a few numerical questions. So let us solve the first question, as this is a turbojet engine problem solving. And this question is very straightforward. We just have to use the basic aptitude and our how to use the formulas that we have found till now. This is a very simple problem. So a turbojet engine consumes air at the rate of 60.2 kg per second when flying at a speed of 1000 km per hour. We need to calculate exit velocity of the jet when the enthalpy change for the nozzle is 230 kJ per kg and velocity coefficient is 0.96. The second is fuel flow rate in kg per second when air fuel ratio is 70:1. The thrust specific fuel consumption. Thermal efficiency of the power plant when the combustion efficiency is 92% and calorific value of the fuel is 42,000 kilojoule per kg. Then the propulsive power, the propulsive efficiency, and the overall efficiency. So we need to calculate all these things. So these are the values which are given to us. From this, we need to calculate these parameters. So let us take a moment to analyze this question and apply the things which I've learned before. And after a minute, I will solve this question. Okay, then let us solve this question. The first part is to find the exit velocity of jet Cj. So the exit velocity of jet can be directly given by the this is from the steady state energy, steady flow energy equation, and that is completely dependent upon the enthalpy difference. The enthalpy change in the nozzle is 230 kilojoule per kg, and we know that the entire change in the efficiency is utilized in imparting the kinetic energy of the gases, whereas that the air the velocity of the air or the gases coming inside of the nozzle, we have assumed it as 0. So that from 0 it will be accelerated to a value of the final velocity Cj, and that is in the expense of the enthalpy change of 230 kilojoule per kg, and that we can find out from this particular formula. So Z is the coefficient velocity coefficient of 0.96, that multiplied into this, when we put in the values, we will get the exit velocity of jet to be 651 meter per second. So that is the answer to the first part. Then the second part is the fuel flow rate. So fuel flow rate is given by the rate of fuel consumption. MF is the rate of air consumption divided by the air fuel ratio. Yes, obviously. So we are given that the air fuel ratio is 70:1, whereas the air consumed is 60.2 kg per second. We will plug in the values and we will get the rate of fuel consumption is 0.86 kg per second. Now we need to calculate thrust specific fuel consumption. So that is given by ma, mass of air, into Cj minus Ca, that is the thrust produced, the thrust force that is produced, and that will be equivalent to this much, 22466.6 Newton, 22 kilonewton. Then the thrust specific fuel consumption is given by the fuel consumption divided by the thrust produced, and accordingly we will get this value of 3.828 into 10 to the minus 5 kg per Newton of thrust per second. So this is a very good uh, way to represent the performance of a engine. So if you give 3.828 into 10 to the minus 5 kg per second of fuel supply, that will produce 1 Newton of thrust. So that's a way of representing the engine performance. Next, we need to calculate the thermal efficiency. The thermal efficiency is given as work output by heat supplied. So work output is the gain in kinetic energy per kg of air and the heat supplied per fuel of air. So we will simply plug in the formula and the values, the Cj square minus Ca square. So you can directly use the mass of since 70 is to 1, you can directly plug in the value of that also, 1 plus mf divided by ma into this. So that will be a better approximation of the entire thing. Anyways, this that won't change much. You can try that in home. And this is the eta combustion. So we have to plug in here eta combustion because mf by ma, this is the mass of fuel per kg of air into the calorific value into 10,000, so that is due to the kilojoule part, and that is the actual heat uh, that is the entire heat that is supplied, but all of the heat is not utilized for increasing the kinetic energy. Some part is lost, and for that we have a efficiency associated, that is eta combustion. So when we plug in these values, we will get a thermal efficiency of 31.39%. So that is the answer to the fourth part. Next, the fifth part is the propulsive power, or the change in kinetic energy simply. The change in kinetic energy or the propulsive power is given by ma into Cj square minus Ca square divided by 2. So that is almost 10.4, or no, 10,433 kilowatt or 10.4 megawatt of propulsive force is generated. Next, we have the propulsive efficiency, that is given by thrust power divided by the propulsive power, and we simply have to use the reduced formula, if you can remember, the 2Ca by Cj plus Ca, and that way we will get the value of 59.8%, which is the propulsive efficiency. And next is the overall efficiency, which is given by thrust work by heat supplied by fuel, and we'll plug in the formula and all the values are given. So we'll just put in the values and we will get a value of 18.78%. So this is the simplest problem that you can have based on the turbojet engine. How do you just have to plug in the formulas and the concepts that you know, and you will get the answers to all the parts here. So it was a easy peasy. And the next question we will solve is here. So in a jet propulsion unit, air is drawn into the rotary compressor at 15 degrees Celsius and 1.01 bar and delivered at 4.04 bar. So you see air is entering in 15 degrees Celsius. So above, the temperature is quite low. Temperature of air is quite low and the density is also very less, although the pressure is same, and that is quite complying with the actual practical conditions. Then the isentropic efficiency of the compression is 82%, and the compression is uncooled, so there is no intercooling. Then after delivery, the air is heated at constant pressure until the temperature reaches 750 degrees Celsius. Okay. Then the air then passes through the turbine unit, which drives the compressor only and has an isentropic efficiency of 78% before passing through the nozzle and expanding to atmosphere pressure of 1.01 bar with an efficiency of 88%. Neglecting any mass increase due to the weight of the fuel and assuming that the R and gamma are unchanged by the combustion. So for air and the gas, we will have to use the same thermodynamic properties. We need to determine that the power required to drive the compressor, air-fuel ratio if the fuel has a calorific value of 42,000 kilojoule per kg, the pressure of gases leaving the turbine, the thrust per kg of air per second, and neglect any effect of the velocity of approach and assume for air R equals to 0.287 kilojoule per kg and gamma to be 1.4. So you see, so the maximum temperature is 750 degrees Celsius. Then the compressor is driven only by the turbine, and both has this uh, isentropic efficiencies, and the nozzle in which the expansion takes place, the final expansion takes place, also has a isentropic efficiency of 88%. The compressor has an efficiency of 82%, whereas the turbine has an efficiency of 78%. And by that, we need to calculate these things. So these are the values that we are given. So just take a moment to analyze this question, and then after a minute, I will solve this question. Okay, then let us start solving this question. So this is the TS diagram corresponding to this problem that you will have. So there is no diffuser part, so only a compressor is present. So that is, the compression is uncooled, meaning the compressor in the compression, the diffuser part is responsible for cooling it because the pressure is increased while the gas actually expands and sorry, it compresses and the pressure is released by that. And since it is uncooled, there is only a one compressor section. So 1 to 2 is the only process, 1 to 2 dash is the only compression process out here, and 2 dash to 3 is the heat addition process. Then from 3 to 4 dash, the heat will be released, expand the heat energy provided here, which increases the enthalpy at state 3. There will be a reduction in the enthalpy while the turbine work is being done. Then from 4 dash to 5 dash, so this turbine work is driving the compressor, and from 4 dash to 5 dash, the nozzle is present, so the exhaust gas from the turbine will finally go through the nozzle where the kinetic energy will be increased, and at 5 dash the velocity will be very high, which will impart the thrust. So that's the whole thing, and we'll solve part by part the entire turbojet engine problem. So first, for the compressor part, we'll have to find the value of T2 dash, and first for that we will compute T2 by the isentropic process 1 to 2, and here we know the pressure difference. P1 is 1.014 and 2 pressure 4.04 bar, and accordingly we will get 1.486 temperature ratio. Finally, T2 is 428 Kelvin, but that's not the actual temperature. We'll have to consider the isentropic efficiency for the compressor, and by that we will calculate T2 dash here. So T2 dash will be given as 458.7 Kelvin. That's the raised temperature. So power required to drive the compressor. So that's the first thing. So simply Cp T2 dash minus T1, and we will get 171.38 kilowatt of power. Then there's air fuel ratio. So for air fuel ratio, so the mass of the total energy imparted from burning the fuel will be equal to the total energy imparted to the air plus fuel mixture. So that is the imparted energy will raise the temperature from T2 dash to T3. So that's the temperature difference out here, and this is the MFC. So from this we will get a relation between MA and MF, and accordingly this is the air fuel ratio, and we know all the values by now, and we can directly calculate the air fuel ratio to be 73.1. Next, the pressure of the gases leaving the turbine P4. So that is P4. So for that we'll have to solve for the turbine and for the turbine part, and we know that, so we can directly calculate. So the work done by the turbine is equal to the work done by the compressor. We can directly equate it, I think. So see, actual turbine work equals the actual compressor work, and from that we will get the value of T4 dash out here. So that's the T4 dash, and we will get T4 dash equal to 852.3 Kelvin. So this is 852.3 Kelvin out here. So that if we know that T4 dash, okay, so we need to find this. So now we'll have to use, we actually have to find T4 in order to use the isentropic process expression. And in order to get T4, we'll have to use the isentropic efficiency equation. So we'll use the efficiency of turbine. Only unknown here is T4 out here. So accordingly, we will calculate for T4 to be 804 Kelvin. And with this temperature, we can use the thermodynamic expression for the isentropic process working in turbine, and we can calculate the pressure P4 since P3 is known. So P4 equals to 1.74 bar out here. So that's how we have done it here. Next is the thrust per kg per second of air. In order to calculate the thrust, we need to calculate this section. So the the gases, the velocity of the gases, if we can know. Let us see how we will do that. So the thrust is only applied due to the enthalpy change happening out here. So if we can directly use the relations to find 5 dash, we can solve for the thrust. We'll see how. So T4 dash by T5, that's the isentropic uh, process part, which is not actually happening, and from that we will calculate T5 out here. So T5 is this. We know T4 dash, we know T5, we do not know T5 dash, but we know the isentropic efficiency of the nozzle, and we will use that in this way. And here if we plug in the values, we will be remaining only T5 dash to find, and T5 dash will be equal to 744.4 Kelvin. So next, C is the jet velocity. then the entire kinetic energy which is increased in the nozzle is directly equal to the work done by the nozzle. So Cp T4 dash minus T5 dash, that is the work done. It is imparting the kinetic energy, and that is actually raising the velocity. So here we have assumed that the velocity at 4 dash is very negligible in comparison to the final jet velocity, and that way we can directly compute this Cj to be equal to 465.5 meter per second. So now we have computed the final velocity leaving the jet. So the thrust force is directly given by 4 kg per second is given by 465.5 meter per second. Why this? Because we have to neglect any effect of the velocity of approach. So the velocity of approach out here 1 is the Ca is 0 out here. So that's why if there would have been the velocity of the aircraft, if we have to consider that, then the thrust force would have been a little bit less, and hence the thrust force now is 465.5 Newton. So that was all for today's session. We have learned about the different jet engines, the turbo jet engine, the turboprop engine, and the ram jet engine. Uh, we have learned the derivation of the or the thermodynamic analysis of the turbojet engine, how we can derive the thrust power, how we can derive the propulsive power, how we can derive the different efficiencies, that the propulsive efficiency, the thermal efficiency, the overall efficiency, the jet efficiencies. Then we have used these concepts to solve a few problems. The two problems out here, one is simply using the aptitude of using the formulas, and the second is related to how to use the processes in a turbojet engine, the thermodynamic analysis part. So in that way, I feel that we have gained some confidence over uh, the the jet engine part and how to solve the problems. So with this, let us conclude this session, end this session. Thank you, and hope to see you in the next tutorial session. Okay then, bye.